Professor Isabelle Gallagher. She has been directrice de l'UFR de mathématiques de l'Université Paris-Diderot. And she has been awarded many prizes, including by prize by l'Académie de Sciences. And the title of our talk is the second sequel of the first lecture.
Thank you very much. Thanks for the introduction. Thank you to the scientific committee for inviting me. It's a great honor to be here. And so I'm going to talk about the sequel of what Laure has been talking about for the last talk. And so let me just start right now with a picture you've seen before. Okay, I guess it's just about where she stopped. So, right, so you want to describe a gas, right, which has n particles. And as she said, I'll just say it quickly again. One way to describe the gas is just to say I know exactly where each particle is at each time and what their velocity is, right? So they'll be moving just in straight lines. This is going to be a very ideal situation where my particles are spheres, hard spheres of diameter epsilon. They're going to move in straight lines until they collide and then just jump off by elastic reflection. Okay. So what you'd like to do is go from this microscopic description up there to the macroscopic description of fluid dynamics. So I'll be interested in the viscous equations, so I need time to be very large, as she told you. You have to rescale time as well, right? So you're going to assume that n goes to infinity, epsilon goes to 0, and that the mean free path, which is 1 over alpha, where alpha was mentioned before, is going to 0. Okay, so as you've been told, this limit here directly is not really known. We don't know how to do that unless you add noise to the system. And we don't want to do that. We want a deterministic system of particles. So we're going to use, as suggested by Hilbert, the Boltzmann equation. Okay, so that's the plan. But we're going to do this in a very simplified way. We're going to obtain in the limits not the Navier-Stokes equation, but just a heat equation. Okay, which is the easiest model you can think of. If you want to write down the Navier-Stokes equation, just throw away every term except for 2, and you get the heat equation. Okay, so that's the plan. So the plan of the talk is, the first thing I'd like to do is spend some time to show you why the Boltzmann, the nonlinear Boltzmann equation, is a good model for the particle system. Okay, why does that equation come up? Okay, so that's going to be totally formal because, as Laure told you, we don't know how to prove that in general for large times. But formally, it's not too hard to get exactly the nonlinear Boltzmann equation. So I'll show you why that appears, and then we'll see in a formal way, but that's very easy to get to make rigorous, how you go from the linear Boltzmann equation to the heat equation, right? And then I'll state the theorem we've proved with Laure and Thierry Boudinot, and try to show you a little bit about the proof. Okay, so let's start with molecules, right? So my molecules are just hard spheres. So like molecule I and J are just moving in straight lines. At some point they hit each other, okay, and then they bounce back by these laws. So of course you don't have to remember these laws. Just you go in straight lines, okay, as long as they don't hit each other. When they do, they collide and jump off. So how do you describe the system? Well, as I said, we want to know exactly at time t how many particles have positions x1, x2, xn, velocities v1, v2, vn. So I'll call Fn the distribution, the n particle distribution of my system. Okay, and this satisfies a simple transport equation, right? Because my particles are just transported through straight lines. But the phase space here is not the whole space in x and v, because you have this exclusion condition saying the particles do not overlap. Okay, so the phase space is a tiny bit complicated because you know the positions of the centers of my spheres have to be far apart, right? Distance is larger than epsilon. So this is my phase space here, the epsilon n times rdn. Rdn is for velocities. And then I have, of course, a boundary condition because I have a bounded domain. Well, with boundaries, not bounded, with boundaries. Okay, well, actually, it is bounded because we'll ask for positions to be in the torus for a technical reason I'll tell you later on. Okay, so I need a boundary condition. The boundary condition is just saying if I have Fn computed at a point, a family of points where xi minus xj is exactly epsilon, if my velocities are going out, I should compute Fn at the same value as if the velocities were going in through the reflection condition. Okay, that's the boundary condition. Okay, if I know Fn going in, I know Fn going out, it's the same. Right, so one thing I'm going to assume here, which is very reasonable, is that my system does not depend on the way I label my particles, of course. Okay, so Fn is not changed if I renumber my Zns. Okay, so that's the second condition here. And now the Boltzmann equation is not concerned with the whole set of particles. It's just telling you how many roughly particles have at time t position x and velocity v. So it's a one particle distribution. Okay, and if you want to find the one particle distribution, what you can do is just integrate out Fn against every quantity, x2, x3, xn, v2, v3, vn, right? And you're just left with a function of z1, where I've written z for xv. Okay, so I just take Fn, I integrate it out against everything except for z1, and that gives me the one particle distribution of my system. Okay, and the question is, what happens when n goes to infinity? Does this converge to f, which would solve the Boltzmann equation? So formally what you do is the following. It's actually very easy. Remember, you have this transport equation on Fn. You know what Fn1 is. You just take the transport equation and integrate it against Z2 till Zn. Okay? So you get a transport equation on Fn1, except that, of course, if you integrate out this transport term, right, well, you have Green's formula that tells you what to do. Okay? So if you do that, what you get is the following. You have to be careful that at some points in the boundary, x1 is touching something, x2, x3, or xn. Right? Since nothing depends on the labeling, I can just decide x1 is touching x2. So x2 is actually x1 plus epsilon something, where the something is on the unit sphere. Okay? And of course, it doesn't have to be x2, so I have n minus 1 possibilities. Right? I've decided it's x2, but it could be anything else. So I have an n minus 1 in front here. And then I'm taking the integral of Fn against x3, x4, etc. So that's actually the two particle distribution. x2 is on the sphere of center x1, and then v2 can be anything. Okay? And then here you have this boundary, this factor here, which comes exactly from Green's formula. Right? So this is explicit, it's sort of formal because I have to justify everything, but that's what you get explicitly. Okay? Now, once you've done that, you're going to remember the boundary condition. Assume that if in Fn2 here, I know that omega dot v2 minus v1 has some sign, okay, which is positive, for instance. It means my particles are actually moving far apart from each other. I can replace Fn2 by the same thing when the particles are going in. Right, because of the boundary condition. So, okay, there's probably a lot of typos here. So it should be v2 minus v1, v2 minus v1. Okay, so if you do that, well, I have two terms now, depending on the size of this factor here, on the sign of this factor. If the sign is positive, I replace my outgoing velocities by incoming velocities, by the boundary condition. If the sign is negative, I don't do anything. Okay? So by doing this, I haven't done very much. I've just used the boundary condition. But one thing I've also done is I've decided what I mean by outgoing particles and incoming particles. Meaning I've decided in some sense in what way time is going. Right? I've decided time is going forward in some directions. I'm saying what happens if particles go apart from each other. If I reverse time, they're going together. Right? So, okay, this is sort of a detail. And now the next thing I do, so let me write this again. So okay, just one comment here. The epsilon is just because the boundary is of size epsilon. And alpha minus 1 just cancels this alpha here, so it's just to make these pretty or not. Okay, so now let's take the limits. So this is totally formal. I'm going to say n goes to infinity, Fn2 converges to some f2. Okay? So then what I do is I use the Boltzmann grand scaling, which tells me that this is exactly 1. Remember, n epsilon d minus 1 was equal to alpha. That was what Bloch told us. Right? So this factor is 1. And then I just cancel out all epsilons I find. Right? And so I get this equation. Okay? Now, as Bloch told you, this is exactly a two-particle distribution, joint distribution, right? F2 of x1, x1, taking the same point. And now the main assumption I'm going to make is that F2 of x1, x2 is the same as f of x1, f of x2. Which means I'm going to assume that my particles are independent. Okay? So I just say F2 is equal to the product of two Fs. If you do that, you get exactly the Boltzmann equation. Right? So that's the equation we saw. So all the indices have been shifted to look more like Lovelock. So 1s are nothing and 2s are 1s, right? So now my variables are v and x, not v1 and x1. So I won't go again through the analysis of this equation. We've seen it a little bit before. But all I'd like to tell you right now is that Law told you there was a problem when Boltzmann introduced this equation. People were very pleased about it. One of the reasons was that this equation is irreversible, right? There's this entropy, when the particle system is not. So what happened and what I did in the last slide, which rendered everything irreversible when it was not in the beginning. What happened is taking epsilon goes to 0, right? Because when epsilon is fixed, I can decide what the sign of my x1 minus x2 dot v1 minus v2 is, right? Because x1 minus x2 is something, it's epsilon omega. When epsilon is 0, there's no more sign, right? So I don't know anymore if time is going in one direction or the other. I can't decide. So when you put epsilon go to 0, you've lost a lot of information. You don't know if your particles are going this way or that way. Right? So that's what happened. So of course, this is totally formal for lots of reasons. One of the reasons that I've assumed everything was independent. I don't know if that's true. And actually, when n is fixed, it can't be true. It has to be true only when n goes to infinity. And also, I've taken the limits without checking anything about bounds or anything. So actually, no one knows how to prove this limit in a rigorous way for uniform time intervals that we've been told. And I'll try to show you why later on. So the thing is, what we want to do is to go from particles to fluids, viscous fluids. So remember, we have to rescale time. So what I need is solutions of this equation which live for a very, very long time, right? So I want t to be an alpha t. Okay. So in what situations do I have very long time solutions for this equation? Well, one favorable situation is if you're looking at solutions which are very close to stationary solutions. Stationary solutions are those Gaussians in velocities we've seen before. Okay. And if your initial data is close enough to such a thing, then your solution is global. Okay, I won't go into details here. Now, the only problem with this thing here is that it's not totally a probability distribution in x and v if x is in the whole space, because it doesn't depend on x. So that's why I'm going to fix, from now on, x to be periodic. Okay? Okay, you could say you could be in the bounded domain, but I definitely don't want to be in the bounded domain, because then you get reflections on the boundaries and things get very complicated. So x is going to be in the torus. Okay, and I'm going to look at this equation and linearize it around stationary solutions. Let's see what happens. So if you do that, you just say f is equal to this m plus a g. Right, all m times m terms cancel because I cancel out the collision kernel. And then I cancel out all g times g terms because I'm looking at the linear equation. Okay, so the two ff minus ff terms become 4 terms. Okay, that's just linearizing. And this is known to be the linearized Boltzmann equation. It's just its name, and we know why. This equation has global unique solutions, at least in a good function space like L2 functions. Okay, but this is not a good framework for us for some reasons you probably will see later on. We want bounded solutions. We want uniformly solutions to be uniformly bounded in time. And so we're going to make this equation even simpler. This is very simple. It's a linear equation, but still too complicated for us. So we're going to remove, in those 4 terms, we'll remove 2 of them. Which 2? Well, remember, when you have v primes here, you're creating a particle of velocity v. If you have v's here, you're losing particle of velocity v. But now, if you look at this term, for instance, it's saying I have a particle of velocity v prime hitting a Gaussian of velocity, okay, and 1 hitting a Gaussian of velocity v prime. Here I have a particle of velocity v1 hitting a Gaussian of velocity v, and v is my variable. Which means in some sense I'm looking at how I'm interacting with a Gaussian. Okay, I don't want to see that. All I want to know is how Gaussians are interacting with me. So I'm only keeping with these 2 terms, where I have g's depending on v and not on v1. Okay, so this is the equation I'm really interested in today. This is a linear Boltzmann equation. So it's even simpler than the linearized Boltzmann equation. It's known this equation has global unique solutions which are bounded uniformly in alpha, and that's good for us. Okay, so the thing is, this equation is supposed to look like the heat equation. And this is quite easy to see in a formal way, and it's not very much harder to prove. So let me try to show you why this linear Boltzmann equation looks like the heat equation. That's very well known. There's nothing new here, but I just want to show you why 2 derivatives come up when you have just this transport equation. Okay, so the 2 next slides are a tiny bit computational. Okay, so you can just close your eyes if you don't like that and wake up in 2 slides. Or not. Okay, so I take the solution to my linear Boltzmann equation. For technical reasons, I divide by the Gaussian. So I get this equation. Okay, you don't really want to know what exactly. Oh, it's exactly the same, so I should pull out the Gaussian. Remember, we have to rescale time. So phi tilde is just phi computed at alpha tau. Now tau is my new time variable. So log is an equation with 1 over alpha, nothing in alpha. I have 1 alpha and alpha squared. Same equation. Right? Now this is totally formal. I want phi to look like the heat equation, the solution to the heat equation. So I'll say phi is something which does not depend on alpha, plus 1 over alpha something, plus 1 over alpha squared is less, right? Just formal. Let's see what happens. What I hope is that rho 0 here satisfies the heat equation. So formally, just take this and plug it into the first equation and cancel out all the higher order terms. The highest will be alpha squared L rho 0. This should be 0. Next will be V gradient rho 0 plus alpha L rho 1. Blah, blah. So you get this. So the last equation in those three equations here is exactly what I'd like to be the heat equation, right? It's like a d tau of rho plus something. I'd like the plus something to be minus the flashing rho. So I need to replace the two terms rho 1 and rho 2 by a function, something that depends on rho only, rho 0 only. Right, so the first thing I check here is that this tells me simply that rho 0 is in the kernel of L. L is this operator here. Obviously, if phi here doesn't depend on V, L is 0. The converse is true. I'm not going to give you any functional analysis or anything here. I'm just telling you kernel of L is people who don't depend on V, which is good because I want my solution, my rho 0 to be a solution of the heat equation, so it should not depend on V. Right? So that's good. Then to get rho 1, it's very easy. I just have to take L minus 1 of this guy here. Am I allowed to invert L? Yes, you can prove that you can. When you compute against functions whose average against the Gaussian is 0. But rho 0 doesn't depend on V. The average of V against the Gaussian is 0, so I can't write this. Rho 1 is this guy plus something in the kernel. Okay, so I have a function. I have a formula for rho 1 in terms of rho 0 plus something in the kernel. Then to get the equation of rho 0, I say, okay, let's integrate this equation against the Gaussian. Rho 0 doesn't depend on the Gaussian on V, so that just gives me 1. Then I have the integral against the Gaussian, and since this is L times L applies to something, if I integrate it out against Gaussian, I get 0. Okay? So this is almost an equation of rho 0. I just have to replace, that was the equation, I just have to replace rho 1 by what I know. Remember, rho 1 was this guy. Rho 0 doesn't depend on V, I can prove it out, and I call B the inverse of V. You get a formula for rho 1. So you have one derivative here, one derivative there, you get the Laplacian. Okay? So from the linear Boltzmann equation, formally, you get very easily the heat equation. This is formal, but it's really, if you know anything about the heat equation, it's really not hard to make this reverse. Right? It's not really a problem, it's been known for a very long time. So what you can prove is that if you take a solution to the linear Boltzmann equation with some data, bounded data, then the solution, when you reach scale time, converges to the Gaussian times the solution of the heat equation. Okay. So now we have the limit equation, we have the heat equation. We know how to go to the heat equation from the Boltzmann equation. Now the question is, how do I go from particles to Boltzmann? Right, so we want to go from particles to the heat equation using Boltzmann, not using any Boltzmann equation. I want to use a linear Boltzmann equation. So the question is, what do I have to do to particles for them not to convert to a nonlinear Boltzmann equation, but to the linear Boltzmann equation? Remember I told you linear Boltzmann is seeing how a Gaussian is hitting me. Right, so what I should do is instead of taking n particles and not knowing anything about them, I should say I'm taking n Gaussians, and I'll just decide that one particle is different. And I'm going to throw that particle in this background of Gaussians and see what the Gaussians are doing to it. And hopefully what they're doing is the linear Boltzmann equation, right, and not the nonlinear Boltzmann. So what that means that I have my system of particles. I think that's sort of important, something you want to remember, is that if you want to get a limit equation, you don't have much choice about the system you're looking at. The system you're looking at is n particles, right? They're going in straight lines, they're hitting each other, and that's it, that's given to you. The only choice you have is what's the initial data you're giving yourself for the system of particles. Okay? So for the Boltzmann equation, you're looking at tensorized initial data, right? So for instance, you should take n copies of one function, okay? And then you have to put the exclusion property, and you have normalized. And that's a typical Boltzmann initial data at the level of particles. Okay, more generally, all you're asking for your initial data is to be controlled by a Gaussian. That's important, and we saw that in Loch's theorem, the Lanford theorem, right? You had a Gaussian on the right-hand side. For one f0, if you have n f0s, you have n Gaussians. F0 depends on x, and its L infinity norm would be c, then you have c to the n, and then you have the exclusion. That's a typical initial data for Lanford's theorem, for a general system of particles. Now what I want is just one particle, and that everything else should be a Gaussian. So I'm just going to decide that particle number 1 has a different density. Okay, so I'm going to take n Gaussians, they'll have density 1, and this particle number 1 has density rho 0. Okay, and that's my initial data for the particle system. That means I'm looking at one tagged particle, I decide it's labeled 1, and I've sort of broken the symmetry here, right? The particle 1 is different from the others. So Fn will be symmetric with respect to every single labeling except for 1. Okay, so I have a tagged particle, tag 1, in a background of particles at equilibrium, and that's my initial data for the particle system. And the theorem we proved with Thierry Boudinot and Laurent Saint-Simon is the following. So assume you have this system of particles with this initial data. right? You take n goes to infinity under the Boltzmann grand scaling, and you let alpha at the same time go to infinity, right? Because I want both limits. Okay? And okay, it shouldn't go too fast to infinity, like a log n, square root of. Okay? Rescale time, then the one particle distribution converges to the solution of the heat equation. In particular, if you look at the trajectory of your particle x1, the rescale time, x1 of alpha tau, at the limit when alpha goes to infinity and n goes to infinity, then that satisfies the Brownian motion, okay, which is normal if you get the heat equation. Right, so for the end of this talk, what I want to do is try to explain how you prove this result. Okay. So, let's see. So, again, what you want to do is start with your n particles, okay? And what Loch has told us is that Lanford proved, well, at least he gave us a way to prove, and I'll try to explain how to do it, how to prove going from n particles, how do you get the limits of Boltzmann equation. And the thing is, in the theorem Loch stated before, the time on which that was true was only 1 over alpha, essentially. Okay? So of course, this is very bad if you want an alpha going to infinity limit, because that means the time is going to 0. So what we're going to try to do is, in the case of the tagged particle, right? So in the case when the initial data is n Gaussians, one particular initial data, the one particular density, we're going to try to prove that in that case, the time of convergence is not only 1 over alpha that we know, not only 1, but actually something can be infinite with alpha, okay? Which means you'll be able to rescale. And to do that, we're going to use the comparison principle with the invariant measure, which is exactly the n Gaussians. Okay, so it's sort of maximum principle. Okay, so that's one thing, and then so that gives you the Lanford theorem in a very long time for this special initial data. And then the other thing you have to do is to check that you do get the linear Boltzmann equation. I told you it should be the linear Boltzmann equation. You have to check that's the correct equation getting the limit. And once you've done that, you're done because you know that linear Boltzmann goes to the heat equation. Okay, so the plan of the talk now is to say, let's start with n particles. Let's see what Lanford did and gets the Boltzmann equation. Let's see why, in my particular case, I get a better convergence time. Let's see why my limit is the linear Boltzmann equation, not the nonlinear Boltzmann equation, and then I'll be done. Okay, so let's start with what's known like as the BBJKY hierarchy from Born, but we love Green, Kirkwood, and Wong, which independently wrote out this hierarchy. So, okay, so we start with our n particles. For the moment, we have any initial data fn0 satisfying the bounds I've told you before. Right? So Gaussian velocities and exponential c to the n. And of course, this equation is set in this domain where I know xi minus xj should always be larger than x. Now remember, if I want to understand fn1, the one particle distribution, I integrate fn against x2, x3, pn. The equation on fn1, remember, had an fn2 on the right-hand side. Right. So now I want to write something rigorous, so I need bounds, so I need to control fn2. Control fn2, I'm going to write down an equation on fn2. Of course, the equation on fn2 will involve fn3. Okay, so you have to write down actually an equation for every fns. Okay. So s is any number from 1 to n. You do exactly what I said before. You just take this equation, integrate it out, this time from xs plus 1, xs plus 2 to xn. Okay, so you get just this transport. Capital V is just a set of V1, Vs. Capital XS is a set of X1, XS. On the right-hand side, you get basically the same term as the one I wrote down slowly last time, right? On the first slide, or almost. This n minus s is telling you, I decide this particle XS plus 1 hitting a particle. Okay, but I had n minus 1 possibilities, living at s plus 1, s plus 2, or n. This is this factor n minus s here. Alpha minus 1 just goes with this alpha here. Okay, then I have the cross-section which came from Green's formula. And then also I have to decide, now I know it's particle s plus 1 hitting someone, I have to decide who s plus 1 is hitting. Okay, s plus 1 I've decided is hitting particle I, so I have to sum from I equal to 1 to s, from 1 to s. Okay, so what you want to remember from this is fns depends on fns plus 1. Okay, and you have this collision integral here, which appears Vs plus 1. You're losing a V in some sense, right? This is costing V. And also, this is costing S, because it is sum from I equal to from 1 to S. When this is large, this is a big number. Now, once you've written that, the idea of Lanford was to say, instead of writing down your PDE and then trying to solve it in some way, which is hard because f and s involve n plus 1, so you don't know. Well, actually, you only have a finite number of equations, right? Because s goes from 1 to n. So you could say, it's okay, it's a finite number of equations, I'll solve it. But n is going to infinity. So this doesn't look so simple to solve. So the idea of Lanford is to say, just change the way of writing down your equation. This is formal. Just write down f and s of t. This is equivalent, formally, to transporting the initial data. ss of t is simply a transport operator, a nonlinear transport operator. It's saying I go in straight lines, when I collide, I have this boundary condition. Okay, so it's a transport operator in my domain with exclusion, ss of t. So you say you just transport the initial data, and then you have a Duhamel term for the right-hand side. Okay, that's just equivalent. Now fns plus 1 at time t1, or t1 goes from 0 to t, I can do exactly the same thing with this. And replace it by the transport of the initial data, s plus 1, plus the right-hand side, which now involves s plus 2. And so on and so forth. So in the end, what you can write is, well, take s equal to 1, because that's the thing I'm really interested in, right? I'm interested in fn1. fn1 is a sum, so I have alpha to the n, because cs plus 1 had, sorry, this shouldn't be, because I think, oh yeah, there was, I forgot alpha too. Alpha and alpha. So each time I do this, I pay an alpha, so I have alpha to the n. I have lots of integrals, 0t, 0t1, blah, blah, 0t n minus 1, and n can be anything from 0 to n minus 1, capital N minus 1. If small n here is 0, I have the first term. Small n is 1, I have just this at time 0 plugged into there, so on and so forth. Okay? So now I've written down fn1 in terms of fn at some level, n plus 1, at time 0. Right? So that's what's interesting with that formula, which is formula not difficult to write, is that you have a series where you've related the solution you're looking for to the initial data you know. Okay? Now the question is, what does that look like when n goes to infinity? So here I've just written down the formula again. And what I'm going to write here is a hierarchy, which is known as the Boltzmann hierarchy, which I find formally by letting n go to infinity. This is formal, and we have to check that we've done things correctly. So formally, this finite sum becomes a series. Alpha doesn't change, but I haven't changed. For the moment, alpha is fixed. And then what I say is that I replace every transport operator, capital S, which is in the domain with exclusion, by straight transport. Remember, in Boltzmann equation, I have f of x1, well, fn2, for instance, of x1, x1. Right? I have no more exclusion, I have no more epsilon. Okay, so I have just transport equation. So I replace each transport operator in the domain with exclusion by the free transport. Then each collision operator here, I just do formally, I take epsilon goes to 0, like we did together at the very beginning, right? So every time I had an epsilon in the formula defining c ss plus 1, right? So I don't, yeah, the formula just before. Every time I find an epsilon, I just put it to 0, and that's all I do. And it can't be anything else, actually. So this is what we decide to be the limiting Boltzmann hierarchy. We have several things to prove. Of course, we have to prove that this is true, so that this fn1 converges to g alpha 1. Okay, which satisfies this. And the other thing we have to check is that the Boltzmann hierarchy has anything to do with the Boltzmann equation. Right? We just know the Boltzmann equation, and now I have just a series. I don't know why this is supposed to look like a Boltzmann equation. Well, again, all this depends only on the initial data. This series is just telling me how the system is evolving. Okay? Now, the initial data is going to tell me what the solution looks like. Okay? Now, I should take initial data just like we've seen before, which is n copies of a fixed function f0, fixed distribution, probability, f0, exclusion, and a normalization factor. You can check just by writing things down that one solution to this hierarchy is simply s copies of the, well, if you put an s here, s copies of g alpha, where g alpha is the solution to the nonlinear Boltzmann. And you just check. Okay? One solution. Maybe there are more, but at least one is that. Similarly, if you take my tagged particle initial data, so I should give it again. Okay, so tagged particle initial data, I have just Maxwellians, and I've changed particle 1 to rho 0 of x1. Actually, I could have put x1 v1 here, but I don't want to for today, but you could do that, which is a little bit more complicated. Right, so if you do that, what you check, again, just by checking things, is that one solution of this hierarchy is simply taking the solution to the linear Boltzmann equation and s copies of it. Okay, and that works. Now, all I need to know to be sure I've done the job I wanted to do is that you have uniqueness for this hierarchy. If I can prove that there's only one solution with any initial data, then I've found it. Okay, and I'm done. Well, I'm not done because I still have to prove convergence. But anyway, to prove the convergence, I'm going to have to prove bounds, and at the same time, we'll prove uniqueness. Uniqueness will come from the convergence proof. Once I have uniqueness and convergence, I converge exactly to what I want. Okay, so again, the initial data is really crucial here. I have a system, and I need to choose my initial data properly to get the right equation. Okay, the limits equation to the tensor version of the solution. Right, so now let's try to go back to my QML formula. So now I've written again the BJKY formula. Forget about Boltzmann. Just look at this here. And the question is, why does this converge to the Boltzmann hierarchy? Now what we're going to do, so that again is a fundamental idea of Lanford, is to try to interpret everything here which is inside the integrals in a more geometrical sort of way in the following way. You start at time t, okay, that's the solution I'm given. Okay, I start at time t, I have just one particle, fnt of z1. Okay? Then what this is telling you is that you're transporting your particle x1. Okay? Up for time t1. When you arrive at time t1, you have this operator c12. Remember c12 is computing f2 at x1, x1 plus x1 omega. That means what I've done at time t1 is I've added a particle sometimes. Right? Add x1, and x1 plus x1 omega. I have a second particle somewhere on the sphere center x1 with some velocity v2. Okay, then I go on with S2, transport, for time t2, then another particle is joined, particle 3. And I go on until time n. Okay? Now, if I look at this in a graphical sort of way, at time t, at time t I have one particle, it's orange, it's diameter epsilon. At the center of my little ball here of diameter epsilon, I have a point, and that's the Boltzmann point, right? Because Boltzmann doesn't have any epsilon. Boltzmann is just a point. Okay? BJKY, I have a sphere. I let this particle evolve by the nonlinear flow for time t1. Now, when you have only one particle, there are no collisions, right? So nonlinear flow and linear flow are the same. So it just goes straight for a velocity v1 until time t1. What I told you is at time t1, you add a particle. Okay, this blue particle is stuck to the orange particle. And then what happens is that when it comes, it's going to hit particle 1, and then they're going to move back one from the other. Okay? So I don't know if it's too clear here, I hope it is. You have your orange particle here, and the Boltzmann one in the center. Now the blue one, you have a slight difference between the sphere here and the little blue point below, which you mightn't see, but I see. Okay, and that blue point below is the Boltzmann point, because when at time t1, when I added my particle, remember Boltzmann is f of x1, there's no epsilon, so I'm at the same point. So then when I go away, after time t1, I have a slight difference between my BJKY center, which is epsilon away from the center of the orange ball, so I have a little difference between my Boltzmann point and my BJKY point. But it's very small, just epsilon. Okay, flow again. Well, at least at time t2, I add a particle. I have the choice. I can add it at the blue or the orange. I decide I add it to the blue, and I flow again. Okay, and so on and so forth. This could go for a very long time. We said that what can happen is that at time t3, I have this white particle arriving, and what it's doing is that it's going to arrive in such a way that it's going to move the orange particle, and the orange particle is going to hit the blue particle between time t3 and t4. So we call recollision. That can happen. If you're very good at billiards, for instance, right? If you have 3 particles on a billiards table, we give you a ball, we say, go hit it, and manage for the orange one to hit the blue one. If you're very good, you can do it. So you're going to say, okay, that doesn't matter. Yes, actually, it does matter. Why? Because when you do this, remember the S of t and BBJKY is a nonlinear transport. If you hit, you jump away. Okay? So the orange ball and the blue balls are going far apart. Now, Boltzmann is just free transport. It doesn't see collisions. Okay, so even if 2 particles cross for Boltzmann, they just cross and don't move. They don't change direction. Okay, so once you've had this free collision, you see the blue Boltzmann center is very far from the blue BBJKY. And you'll never be able to prove that BBJKY looks like Boltzmann. Okay, so you have to kill recollisions. If you have recollision, you can't prove the convergence. Okay? And that's sort of normal because remember, Boltzmann's idea is to say everything's independent, okay, after a collision. But of course, they're not again, because here blue and orange hit each other again, so not independent. You really have to avoid this. So the whole idea of Boltzmann's proof, Lanford's proof of Boltzmann's theorem, is to say that these recollisions can happen, Okay, because if you have billiard tables, you can do it, but it's very difficult, at least when n goes to infinity. There are vanishing probability. Okay, more precisely, what you're going to do is the following. So again, this is very geometrical. Let's pretend you have, okay, making things simple, you have 4 particles, okay? They're moving around in straight lines, going far away from each other, and you add one. Okay, what you have to do to add one, and for it to hit one of the 4 others. Again, you have to be very good. Okay? What you're going to do here is you're going to avoid this. This is very geometrical lemma, which is not very hard to prove, to say it costs a lot to be able to point in a good direction. Okay? Especially when epsilon goes to 0. The particles are smaller and smaller, it's going to be more and more difficult to hit a new particle which is already moving somewhere, which you know. Okay? So as long as you have a finite number of particles, it's not too hard to avoid recollisions. You're just going to be careful. Each time you add a particle, you're going to remove a tiny bit of phase space to avoid this new particle hitting any other one for any future time. Okay, so that's easy. When epsilon goes to 0, the measure of this part of phase space is very small, and so you can prove your result. The problem is that I had a series, right, an infinite series. So actually, epsilon is going to 0, but n is going to infinity. And if you have many particles in my billiard table, it's going to be harder and harder to avoid them. What you should do is first restrict your problem to a finite number of particles, or almost finite. And on this, you do your geometry, you're done. And then you have to kill the rest, the remainder. Okay? You have to say my series from 0 to n minus 1. Actually, it's a series from 0 to k. And the remainder of the series is small, because my series converges. If my series converges, to prove that, all I have to prove is a uniform bound on the solution. Right? But the problem with proving a uniform bound is, remember, as I told you before, to write down fns in terms of fns plus 1. On the right-hand side, you have an s, because you have a subharmonic to s. And on the right-hand side, you have a vs plus 1, remember, on the collision kernel. So you're losing velocities, you're losing s's. Right? So if you want to write down an estimate which is okay from a PE point of view, you have to take into account those losses by using, for instance, an exponential weight in your norms. Okay, this is a technical part of the talk, but on my phone, just one slide. Okay, so you take fns, you multiply it by a weight, and then you use a sort of Cauchy-Kovalevsky argument which says, as time goes on, you can control everything, but the weight, you're going to have a linear loss. Some constant, c, it doesn't depend on much, and alpha especially, it's alpha is on the right-hand side. Okay. So you can prove rather easily that if your initial data isn't such a space, which is exactly a space actually Rob showed you at the beginning for the initial data, okay, mu and lambda, not beta. If your initial data is in this space, then the solution will be in the same space, but unfortunately your coefficients here, lambda and u, are going to decay linearly in time. So that forces the proof to stop when this coefficient gets to be 0. That's 1 over alpha. Okay? So this is the reason why Lanford's proof only works for very short times, is because of this. Which is not a very good reason in some sense, because if you had, for instance, you were looking at Maxwellians, everything would be global because you know the collision kernel is 0 for Maxwellians. Here, all I'm using in this argument is that I have an equation like dtf is equal to f squared. Right? It's exactly the same, which is stupid because Boltzmann is not f squared. But okay, we don't know how to do anything else. We don't know how to use a structure as a collision term at this point to prove anything. So once you've done that, you have this theorem. So this theorem has a long history. Of course, it's Lanford who gave the whole proof up to some details, and the details were added by a number of people throughout time. And so we have this paper of Saint-Raymond and Aug19Tue where we've proved this in this setting, as well with in the case of potentials, actually. Everything I'm saying today is true if you have a compactly supported repulsive potential with a few assumptions. Okay, and it works, it doesn't work exactly the same way, but it works also. So this is essentially the theorem Laure told you. You have initial data with the bounds I gave you. Then you have a convergence on a time 1 over alpha. Moreover, which is interesting for the rest of what we're going to do, is that you have a rate of convergence. Okay, so it doesn't just converge to the solution of the Boltzmann equation. You have a rate of convergence, some power vector. Now, to finish, I'd like to explain why, in the case of a tagged particle, things go better. Okay, why is it not 1 over alpha, but anything more? So let me recall the initial data for the tagged particle. So I have here this guy, which is just n copies of the Gaussian, the exclusion, and the normalization factor. Okay? And then I have rho 0 of x1. I've decided to change particle 1. The only thing I'm going to use here is that rho 0 is bounded, because I've decided it was bounded. Anyway, it is because it's bounded. And so I'm just going to control this by the Gaussians times rho 0 and infinity. That's trivial. Now, the only remark I want to make here is that, remember, Gaussians are stationary solutions to the UV equation. Right, you can see that's easy. Okay? They don't depend on x. So the UV equation is set in this space here. So you know that this guy is a global solution to the UV equations. It's a stationary solution. The UV equation satisfies the maximum principle. Okay? So the solution associated with this data here is controlled by the same thing. That's just the maximum principle, because the right-hand side is a solution, and this left-hand side is a solution. But this is very good because it's saying that if you take marginals, okay, you have a tiny computation telling you what marginals of this guy are, but that's well known. And what you can prove is that the marginals of f and s are controlled by exactly the same Gaussian with no loss and same loss. Okay? And this is crucial because you don't have this beta minus something, minus c alpha t, right? You have a global control with no loss. So once you've seen this, you haven't finished the proof, but you're pretty sure you'll be able to finish the proof because you know now that what stopped Lanford from proving the result was that he had to stop because everything was going wrong. The weights were going to 0, right? But for us, the weights are just the same for all times. So then how do you use this information? Well, in the following way. So that's what we did with Laure and Thierry to end the proof of the theorem I told you. What you do is the following. You say, okay, I want to prove my result in a time 0t. Let's hope t can be as large as I want. We'll see. So I give myself a small t. Hopefully t will be as large as alpha, so I can rescale. And I cut out my interval in intervals of size h. And h will be very small later on. It's basically the Lanford size, 1 over alpha. Okay, we'll see that later. But what I'm going to do is write down the usual arguments. So I just go backwards. So I have time t. I'm going to time 0. I'm using my geometric composition. But I'm only going to keep at each time step, I'm going to throw away any super exponential tree. What's a tree? Well, a tree is just what I drew before, right? Having collisions, more and more particles. Why is that? Because on a unit time, if you take alpha equal to 1 for a second, on a unit time interval, a particle is going to hit another one, roughly, right? So the number of particles you're going to create on the time t is exponential. Okay, that's very probable. But having something super exponential is not very probable. Okay? So, okay, my exponential factor is a. A is going to be very large later on. That's totally technical. So I'm going to call a good collision tree any tree such that when I go from t to t minus h, t minus 2h, blah, 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 all my collision trees, the number of collisions I'm looking at is smaller than a to the k. If going through this, at one point I get a tree which is too large, I just throw it into a remainder. So I decide it's a remainder. Okay. So my good collision tree, which is symbolized by that, is Lanford on time h, Lanford on time, another time h is Lanford, blah, 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 but only for exponential trees. And here is I flow, and if I stop at some point and I see my tree is too large, I stop flowing. Okay, why is that a remainder? Well, simply because every time you have a collision kernel, you're paying a constant to the power of the number of terms you have. So double exponential in k, actually. K is time step. Okay, but on some small time step, I have too many particles, but the time step is small. So I have a time step to the power of the number of particles I derive at. Okay, this is very small. And I know I can stop my tree at this point here, and I know the size of my solution here is the same as the size of the solution here. So all my constants are the same. So I can do a sum. Okay, it looks stupid, but simply you're going to sum your errors, and actually you're going to have essentially a geometric sum of h to the power, the number of particles, h to the power a to the power k. I'm going to sum that over k. Okay, but the constant in front of that is the same at each time step because my solution has not grown at each time step. So at the end of the day, if you decide that your h here is 1 over alpha, which makes Lanford's proof work, okay, and a small parameter gamma in front of it, then your remainder will be the sum of gamma to the a to the k. You sum over k's, that's gamma to the a. Okay? So your remainder is as small as you want if gamma is small. And then so that kills the remainder, and now you're just back at studying this thing here. And on each of the time steps, you're going to do Lanford's argument. And since we know now that the Lanford proof can be made, you can quantize the error, you can start optimizing all parameters, the error term, the gamma, whatever, and you get this estimate. I'm going to finish here. All you have to notice here is that you have an alpha on the right-hand side, that's very bad, alpha goes to infinity, but you have log n at the bottom. Okay, so as long as alpha, a can be as large as you want, as long as alpha is smaller than log n, then this goes to 0. Okay? Then you rescale time to get the heat equation, remember? You have alpha tau, so you'll have tau alpha squared. If alpha squared is smaller than log again, it still goes to 0. Okay? And that basically ends the proof. Thank you.
Any question or comments?
You don't explicitly use chaotic hypothesis here. You don't explicitly use chaotic hypothesis here.
No, the only thing you use is the uniqueness result. Chaos comes from uniqueness. You have it initially, right? You're chaotic initially, and then when it goes to infinity, by uniqueness, your solution is chaotic.
Any other questions? If not, let's answer speaker again.